Hello POPL, thanks for joining this session on typed compilation with Nameless Labels. This is work that I've done together with Robbert, Krebbers and Eelco, Visser in Delft. Let me jump in and show you what it is that we're after here. So here you see a compiler written in a functional language in a monadic style. So by writing it in this monad compiler, we can just write some instructions away, as we do here on the third line, just write a conditional jump, and we don't have to worry about concatenating these fragments of output, because that's all handled within the bind of this monad. And what we get that way is a definition of this compiler which looks almost declarative. It almost looks like the compilation template as you would find it in any textbook on compilation. Now, it's basically this that we want to do, except we want it to be intrinsically typed. And what we mean by that is that we want bytecode to be a dependent type, so that we can only construct output that is well typed. And that allows us to eliminate many bugs in the compiler, because we have this intrinsically have this important theorem of the compiler that it's type correct. Well, this is still a relatively low verification effort, because we only need the static semantics and not the dynamic semantics of the source and target language, as we would need to have for a fully functionally verified compiler. Now, what is the output of a compiler like? It's a very simple language conceptually. We just have a list of instructions, but we have some global binding. We have these jump instructions which reference other instructions using a label, and we'll see that this is the crux. This is the difficult part of intrinsically typing bytecode. How is bytecode typed? Well, you can type instructions using the pre and the post type of the stacks. So here the push through works in any stack phi, and then afterwards you will have a stack bool const phi, etc., etc. It's been shown in previous work already by James McKenna and Joel Wright that if you have a dependent type indexed by pre and post stack types for instructions, then you can actually write a very nice intrinsically typed compiler in a suitable dependently typed language, but they use a structured representation of control flow. So that means that they basically had one instruction, if then else, which took two bytecode sequences for the branches. And what we're after is this flat representation of bytecode using labels to encode control flow, because that's eventually what you want your compiler to produce. What are the rules that labels have to abide by? First of all, every label that we jump to must in fact be bound, otherwise we have an ill-bound jump. And every label that we define must be defined at most once, otherwise we have an ambiguous definition. Now, when both of these are satisfied, we talk about well-bound labels, and it turns out to be very difficult to enforce well-boundness intrinsically. The intuition behind this is that this is a global form of binding. So this is really not scoped by the AST. These are all forward jumps, for example. Contrast this with lambda binding. And that makes the typing anti-compositional. In an intrinsically typed setting, we really want our typings to be compositional, because we're going to really treat bytecode as data. We don't want to do any additional proofs on top of just putting our data together. Okay, so how is bytecode normally typed when they're using named labels? You get one of these contextual typings where you have two contexts, a linear context E and a normal context I. So E is a map of defined labels, and I is a global context of all labels that we can reference. And then we can enforce the two rules of well-boundness. First, using this proof obligation in the middle, which ensures that we define labels only once. This is disjoint map composition. And then we have a second top-level condition saying that I is a submap of E, ensuring that every label that we jump to is also bound somewhere. Now this is a non-compositional typing because this is really proof obligation. Whenever we compile two expressions and we want to put the fragments together, then we have to prove that they only define disjoint labels. And similarly, this top-level inclusion condition doesn't break down easily into something that we can prove locally. Now, rather than pursuing this approach with named labels, which appear very global and anti-compositional, we'll do something different. We'll pursue a representation of labels that is nameless, and we'll get a co-contextual typing of bytecode. And then we abstract over all of the co-contexts that we get using an embedded separation logic, which is the second thing I show. And finally, I show how we construct functional abstractions for doing compilation on top of this logic. So this is basically the representation of bytecode that we'll be looking at. Rather than having names in these reference and binding positions, we have nothing. I'll color these reference occurrences as purple and these binding occurrences as green. And then what is actually going to contain the information of how binding works? Well, we're basically going to have these trails actually in the spine of the AST. So if you want to know what this label jumps to, you have to follow these breadcrumbs that you find in the spine and walk towards the instruction that is targeted. And we'll actually enforce that these paths are going to be the shortest possible paths, which makes this a very compositional representation. How does this work? Here we have the co-contextual typing rule for the bytecode that we'll be using. We use interfaces denoted by case, which are basically pairs of a list of stack types that represents the exports and a list of imports. These are going to be tight. What I mean by that is that this list of exports only contains those labels that the outside world is actually going to use, and this list of imports is only those labels that we are actually referencing in this fragment. Now, the typing rule looks very similar with this notion of interface composition in the middle, but that's a little bit misleading. In fact, this is very different because this composition is going to be trivial whenever we want two fragments to be non-interfering. So if we separately compile two expressions and they are not interested in the labels that that the other part defines, then we can put this together. We don't have to prove anything. It's trivially fulfilled. But when do we have to do some work? Whenever we want these two parts to actually have interacting binding, then we have to give a non-trivial proof term there. Now, coincidentally, that last case is exactly the thing that is very intentional, the thing we want to express when we write a compilation function. So this matches very well with the program that we're going to write. Okay, so let me talk you through an example. So here we have the composition in this node, with on the left hand side we have a single export of a label. So that happens to be typed int const phi and no imports. And the right hand side of this node is just the empty list, so no imports, no exports, the empty interface epsilon. And this composes simply by adding up the exports and the imports for the whole node. Now, similarly, here we have a single export for this push instruction that is labeled, which gets added up with the interface of the tail. And now we get to the interesting node. Here we have a jump on the left hand side, and this jump is supposed to go to this NOP instruction. So we have a single import of type int const_phi. And when we compose that with the interface of the tail that we just constructed, then we can resolve this import using this export so that the import doesn't appear in the composite. And we can also choose to hide this export now that we've used it, so it also doesn't appear in the composite. Now this is actually very important idea if you want to be compositional. You can hide these labels from the outside world. Here we have a very simple composition. We repeat the exercise with a single import getting resolved by the last remaining export, and we end up with the empty interface on top. And no top-level proof conditions, so that's very important. Now let me just briefly stress what it means that we have the empty interface here. It doesn't mean there are no labels at all in this program, as it would in a contextual typing. It merely means that there are no exports and no imports. So this is a self-contained fragment of bytecode. Now, the next problem we face is that we now have this very complicated representation of binding. So here we zoomed in all the way on one of those nodes, and we see that we see the interfaces of the head, the tail, and the composite. And some of these imports are getting resolved by exports of the tail and vice versa. And the remainders are added up to be the interface of the composite. So there's a lot of information here. If we have to manually construct these proof terms, that's going to be very human unfriendly. So we have to do something more clever to program with this and write a nice compiler. So the next thing I'll show you is how to abstract over these co-contexts, these interfaces, using a embedded proof-relevant separation logic. Now, how do we construct this separation logic? We do this by proving that interface composition is a proof-relevant separation algebra. This is a notion that we've introduced in last year's CPP. And what that means is that we can read interface composition as some sort of monoidal composition. But it's a very general notion of monoidal composition because this is a relation that is not necessarily functional. So we can have multiple z's such that x composed with y makes z. And it's also a proof-relevant relation. So there are multiple ways in which x and y can make a single z. Now the separation logic construction then is very normal, except that we construct it in set because everything is proof-relevant rather than in prop. So our objects are predicates from interface to set. And then the most important connective is the separating conjunction, which is itself a predicate over interfaces, over an interface K. Then it existentially quantifies over two sub-interfaces K1 and K2, such that K1 composed with K2 makes K, and it has two projections, P of K1 and Q of K2. Then we also define these primitive predicates for saying that the underlying resource or interface is empty, or exactly the interface that we give. And then we have the pointwise implication between two predicates. And finally we have two embeddings, the universal closure of a predicate and the empty closure of a predicate. Now, I'll show you how this is useful. Here we have again the typing rule for the cons of bytecode in the co-contextual style, and now we are going to embed this into Agda as a as a dependent type. So we have here type indexed by two stack types, being itself a predicate on an interface. Now the nil is the bytecode that doesn't modify the stack. It is embedded using the empty closure because it has the empty interface, doesn't have any imports and no exports. And the cons is the separating conjunction of an instruction and a bytecode tail with a matching stack type. And the separating conjunction hides the separation of the context of the resulting bytecode into two existentially quantified subcontexts and also hides the composition of these co-contexts or interfaces. Now, how do we deal with label references and binders in the setting? Here we have the co-contextual typing rule for the goto. I haven't shown you this before. The way we deal with binding is in a co-contextual styles, but just by stating that the import context contains a single label with the right type. This is very reminiscent of the Codebruin encoding of lambda binding by Conor McBride. And this is work that highly inspired the work that I'm presenting right now. And in Agda it looks like this. We use the own predicate to say that the interface is exactly a single import. Because of the way that we've constructed this algebra, this value that inhabits this type is going to be a relevant reference. So we can duplicate it if we want to do multiple jumps, but we cannot throw it away. Now, for binders, we do something similar, except that we now just say that the export context contains a single label of the right type. And in Agda, we deal with this similarly using, again, the ownership predicate, using the single export here. And now the underlying algebra is going to ensure that this is a linear binder. So we can't even duplicate this, which will in turn ensure that labels are only bound once in the output. Yeah? Okay. Now we come to a very special rule of this logic. There is a particular way in which we can put together a linear binder and a relevant reference of a matching type using the fact that our logic allows us to resolve an import using an export of the same type, and also allows us to hide this export in that case. So this composition has the empty interface, which we see here again in the using the empty embedding. Now, why is this an important constant? Well, what we've done here is we've constructed a pair of a binding occurrence and a reference occurrence that are for always bound together. So even if we take this apart and put the reference in one place in the output and the binder in somewhere else, then these remain connected. And as such, this basically just implements our fresh label primitive for compilation, and it does so without state. That's very interesting. Now, I'll show you how to use this in a bit, but first let me show you how we construct the compiler monad on top of this logic that I've presented. So here we have its definition. A compiler is just a writer monad because we don't need state anymore to generate new labels. So it's just a separating conjunction of the output, the bytecode, and the value in the monad. And what this means is that compilation is going to be really compositional, because if we separately compile two expressions, there is now no order imposed on these compilations by the threading of the state. Now, our compiler itself is going to be typed as taking an expression of type A and then returning a compiler which is typed using the stack invariant of expression compilation. So what this means is that starting in any stack typed phi, the compiled code is going to do all kinds of stack manipulations, but in the end it will just leave behind a single value of type A on top of the existing stack. Now, and then here we have the empty embedding again, which means that compilation is going to produce self-contained bytecode. In what sense is this compiler a monad? Well, first of all, it's going to be a parameterized monad in the sense of Bob Atkey's parameterized notions of computations. So it has these indices that match the underlying output. And then it has a bind that makes use of the adjoint of the separating conjunction. So this is the magic wand, or the separating implication. And what that ensures is that the continuations in our monadic computation can actually close over labels. So that's important that we have this bind. And then we have the operation code, which takes a single instruction and produces, just puts that in the output. And then we have the operation attach, which we can now type very precisely, saying that it takes a linear binder, represented again using this ownership predicate, that matches the type of this compiler computation, so that we can actually attach this label to this output when we produce the output of this attach operation. Now this brings us to the definition of the intrinsically typed definition of the compilation of this conditional. So this is the typed variant of the untyped code that I've shown you on the first slide. And we haven't touched upon all the details of this code, so you'll have to look at the paper for some of these details. But I wanted to point out a few things, and I wanted to show you this. So here we construct a new label, and we do this outside of the monad. So this is just a let binding. What we get is a reference occurrence and a binding occurrence, as I've talked about. And in the middle of this separating conjunction, we find this separation witness, which exactly explains in what sense this reference occurrence is bound to this binding occurrence. Now, because this is such an important bit of information, we cannot just leave this behind when we use the reference occurrence here. So rather, we carry across the binding occurrence with, again, this separation of interfaces in the middle using monadic strength. Now, when we do this systematically, we keep everything well bound, and Agda can see that in the end we have bound all the labels that we jump to, and it also knows that all of the bytecode that we produce is well typed. So there was no, if we forgot this attach operation, then Agda would not accept this code. So what we have here is an intrinsically typed definition of the compiler. We don't need a separate proof of its type correctness. We've dealt systematically with interface compositions, and we don't even need state to implement this anymore. A bit of future work is to get rid of this manual handling of the separation witnesses using monadic strength. So as you can see, that gives a little bit of syntactic noise, which you can see as proof work in our intrinsically typed definition. And it would be nice if we can have a little bit nicer surface syntax. Okay, so what else can you find in the paper? I've shown you in this presentation the compilation itself, but we do in fact an entire case study going from an intrinsically typed co-contextual source language all the way down to bytecode. And we have a stage that removes NOP instructions from the output, so that's a bytecode transformation, and we have a stage that assembles this, eliminating this nameless representation of labels. Then we have a lot of generic constructions. So the writer monad, for example, that I've shown you is generic in the underlying separation algebra. So this is a library for doing proof-relevant separation logic in Agda that we've written for CPP last year and extended for this work. That is all I wanted to show you in this talk. I hope that it was clear. If you have any questions, or if not, just please come see us also in the live session at POPL. All of the important artifacts and the paper preprints you can find below this link.